Okay, so in our previous sessions, I have discussed various derivations related to properties of liquid. Okay, so we have discussed particularly in properties of liquid, we will have surface tension, viscosity, then Pascal's law, that is the hydrostatics. You will have equation of continuity, and then you will have Bernoulli equations. Okay, so those are the major things. So what I have mentioned here are like mm, different concepts what we have already derived, sir, like Bernoulli's principle, okay, which is basically conservation of energy. There are three components of energy: pressure, velocity, and height. Okay, pressure energy, mm, kinetic energy, and pressure energy, kinetic energy, and potential energy. Okay, that remains constant. And then surface tension, viscosity, what is streamline flow, and Renault number concept, and all that. Okay. So we are discussing that this pressure is nothing but H rho g, and the unit of pressure is Newton per meter square, which is Pascal. And then what is the Archimedes principle also? Well, so as per Archimedes principle, when a solid body is immersed partly or wholly in a liquid at rest, it loses weight, which is equal to the weight of the liquid displaced by immersed portion of the body, solid body. Okay. So suppose you you have some liquid. Okay. So if you have some, the body is immersed in this. Okay. So this uh, there will be loss of weight of this body. Okay, that is because of the buoyancy force. Okay, so the loss of weight will depend on the volume of liquid that is displaced by the body. Okay, so equal to weight of the, so loss of weight of this body is equal to weight of liquid displaced by the body. Okay, so let us say this weight of this body is W. Okay, but because of buoyancy, let us say the height of liquid, height of this object, or this rectangular object which is immersed inside the liquid, let us say it is h. Okay, so this h mm, so let us say, yeah. So typically, let us say this volume of this body is V. Okay, okay. So let us say the total height is h, and let us say h by 2 is immersed inside this liquid. Okay, that means V by 2 of this body is immersed. Okay, half the volume. So this V by 2, half the volume is immersed. Then you have to multiply the density of this liquid that is displaced. Okay, that is the catch point here. Okay. So V by 2 into the density of the liquid which is being displaced. Okay. So like the effective weight, what you will see is weight of the body minus volume of the liquid. Here in this case it is V by 2 into the density of liquid. So that will be the apparent weight, right? Yeah. So there is, because of this weightlessness you will find. Okay. So when a body floats in water, so if the weight of the displaced, if the displaced weight is more than that of the weight of liquid displaced by the body is more than the weight of the body, then it will float, right? Yeah. Because it will create a upward force which is more than the actual weight.
Yeah.
So when the ship is there, so the amount of liquid it is displaced, the weight of the liquid that is displaced is more than that of the weight of the body. That's why it is putting a upward force. That buoyancy force is upward, whereas weight is downward. Okay. So you have a weight downward and you have a buoyancy force upward. So if this buoyancy force is more than the weight, it will float, right?
Yeah.
So this is buoyancy force and this is weight.
Yeah.
So there can be some numericals on Archimedes principle you might have done. Okay, in class 9-10 also it was there. Okay. So that is about pressure is equal to rho gh, and pressure at any height h is equal to rho gh plus the atmospheric pressure. Okay. So the pressure excess of the atmospheric pressure is called gauge pressure. Okay. And then there are some formulas related to surface tension. Okay. So you have surface tension. Okay. So surface tension is nothing but your force divided by the length or energy divided by area. So amount of energy required to additionally that to change the area by the change delta change in surface area.
Yeah.
Okay, that is the energy per unit area or force per unit length. So the unit of surface tension will be Newton meter. Okay.
Yeah.
So that is one formula related to surface tension, and then there is excess pressure inside a liquid drop. There are some formula. So if you have a liquid drop, the pressure inside the drop is more than that of the outside. Okay. So you have some pressure acting inside the liquid drop. Okay. So this extra pressure delta P as compared to the outside is nothing but 2s by r. So just remember this. And if it is a soap bubble, that delta P will be 4s by r.
Yeah.
Okay. So you can correlate this surface tension is nothing but Newton per meter. R is the radius. Okay. So r Newton unit will also be meter. So Newton meter by meter. So which will be Newton per
Meter square.
Okay. So these are some of the key formulas related to surface tension. So this excess pressure and all that. Okay. Then you have capillarity related to surface tension. You have capillarity, capillary rise. Okay. So there will be some governing formulas related to capillary rise. So that formula, like say, if you have a capillary tube like this, and you have this, then this height. Okay. So this height. So this is your radius of this capillary tube. Okay. So if this is your radius of this capillary tube. Okay. So your height, this capillary rise is equal to, the formula is 2s cos theta, 2s cos theta divided by r, rho and g. Okay. So you can check actually. This is Newton per meter, and if you you will end up with this height. Okay. So to find out a capillary rise, you need to know the surface tension. So surface tension of liquid is a property, it depends on temperature. Okay. Yeah. Mercury has very high surface tension. So if your surface tension is very high, it will not weight the surface.
Yeah.
Okay. So that I have discussed in the surface tension chapter, and it is available. So surface tension, and then R is the radius of this capillary tube. G is acceleration due to gravity, rho is the density of the fluid. Okay. Angle theta is your angle of attack. Okay. Angle of contact. Sorry. This is theta. Okay.
Yeah.
Which is your angle of contact. if theta is less than 90 degree, cos theta is positive, so h is positive.
Yeah.
So in this case, h is theta is less than 90 degrees, so that's why h is positive. But when theta is more than 90 degree, this it will be like how it will be like this capillary tube. Actually, you put it inside a it will be something how it will rise. So you have a bigger you have a like you have a container like this. So in this container you have this capillary tube you are going to put, right? So when you are putting a capillary tube, it will the water will rise. So this capillary action is very very important. This in our trees and all, through by capillary action through your root, water rises to the top and all.
Yeah.
So that's why if so that means what you can see here, the h value is inversely proportional to r. What does it indicate? That means the thinner is the tube, more is the height, more is the rise. Okay, so so that is about capillary rise. Okay, and just remember that surface tension is a property of a liquid. Mercury has the highest surface tension, and this soap water has lesser surface tension as compared to normal water. And with increase in temperature, the surface tension decreases.
Yeah.
So that is the reason why hot food you find it to be tasty, because its surface tension is less, so it will weight more surface. It will come in contact with more surface of our tongue. That's why you find it to be tasty. Okay. So this is about different formulas related to surface tension. Okay. And if theta is equal to greater than 90 degree, it will be something like this. Okay. So you have the tube, and when this happens, it will not be a concave surface. Instead, it will become a convex surface. Okay. So it will become a convex surface, and you will measure the angle like this. So this is the angle actually. This is the angle of contact, which is the obtuse angle. Okay.
More than 90.
More than 90. Okay. So the definition of angle of theta also you can see. Okay. Okay. So these are things about surface tension. Okay, and capillarity, and then Bernoulli's equation. Okay. Bernoulli's equation. Okay. So we were drawing, like, say you have a tube like this, and you have a tube. Okay, so this is point 1, this is point 2. Okay, so this is my point 1, point 2. Okay, so what we write, it is like pressure 1 plus half rho v square. Okay, plus pressure is equal to rho gh. Okay, so this will be consistent unit. Okay, v1 square gh1 is equal to p2 plus half rho v2 square plus rho g h2. So what is this h1 and h2? If you take this as datum, so these two are the height from the datum. Okay, and here at this point the pressure is p1 and the velocity is v1. Okay, and at this point pressure is v2, velocity is v2. Right. So this is so how do you remember it? You just remember that your pressure, earlier you have studied pressure is nothing but your rho gh. Okay, so and then this is kinetic energy. Okay, so okay, so here this is energy actually. So this energy mv square, right? So sorry, this was mgh, right?
Yeah.
So mgh, when you divide it by volume, it becomes unit volume.
Yeah.
Right? So this becomes equal to rho gh, right?
Yes.
Similarly, half mv square when you divide it by volume, it become half rho v square. So these two things, if you remember, pressure you can just add to it. Okay. So this you can also correlate. Rho gh is pressure, so pressure. Only thing you may get confused is mv square.
Yeah.
So because other
velocity
two,
and volume v.
So because other two are divided by v, here also divided by v. So you will have consistent unit. Okay. So this is about Bernoulli's equation. Okay. So so this is this kind of a tube, but if it is a horizontal tube, okay. So let us say you will have some questions like say you will have a tube like this. Okay. So you have a tube like this and it is a horizontal tube. Okay, if it is a horizontal tube, this term will get cancelled. Okay.
Height is same.
Height is same, so it will become P1 plus half rho V1 square is equal to P2 plus half rho V2 square.
Yeah.
So this is for a horizontal tube. And these are the different heads. Okay, so this is pressure head. This is called velocity head, and that is called datum head. Okay. Okay. Rho gh. Okay. Rho gh is the datum head. Pressure head, gravitational head, and velocity head. Okay. So head means it has to be, the unit you should be in meter. Okay. So everything if you divide by rho g, then only you will get it as head. So pressure head means it will be P by rho g. Okay. Right? And because if you divide this by rho g, you will get H1. So every term if you divide it by rho g, then only you will get head. So P by rho g is pressure head, right?
Yeah.
Pressure head.
Velocity
and
head.
H1 is the datum head, and V square by 2g. V1 square, V square by 2g.
Yeah.
Okay, you
rho
are
will get
dividing it by
cancelled.
rho g, so V square by 2g is your velocity head. So everything is, so you know V square velocity head. So these are the three heads combined together will be the total head at any point of time. That is the total head. Right, so that is Bernoulli's equation, and this is Bernoulli's equation, and then there is something called Toricelli's theorem. Okay, so what is that Toricelli's theorem? So velocity of liquid flowing out of a narrow hole, or the velocity of efflux at a depth h below the free surface of a liquid v is equal to 2gh. Okay, so it is something like this. Suppose you have a container like this. So you have some hole here. Okay, so the water will come out like this. It will try to come out if you put a hole. So let us say this height of this water is equal to small h. Okay.
Yeah.
So this velocity at which it will come out, so this horizontal component, this velocity will be called velocity of efflux. Okay.
Yeah.
So this is v. So this v is nothing but square root 2gh. Okay.
Yeah.
So it is nothing like half mv square. Okay. So so mgh is equal to half mv square. So what happens? The datum energy, the potential energy get converted to
kinetic energy.
Here at this. So mm cancels. So v square is equal to 2gh. So v is equal to square root of 2gh. So this velocity at which the water will come out of the container, that velocity is called velocity of reflux, and this principle is called Toricelli's theorem. Okay.
Okay.
Toricelli's theorem. Okay.
Yeah.
So this is one another concept in on your properties of fluids. Okay. Okay. Then there is Venturi meter. So this is just the Venturi meter will be something like this. So you will have Okay, so this is something like there is a constriction. Okay, so this location you can call it as, so you will have two cross sections. Okay, so you will have two cross sections, one here like location 1 and location 2. Okay,
Yeah.
so because the area here the area is reducing, so the velocity will increase. So because the velocity is increased, the pressure will, here pressure will be little high and here the pressure will be little less.
Yeah.
So if you put so the pressure will be little less. So there will be a difference between the height. Okay, so there will be a difference between this height and this height. Okay, so if you measure the height, there is a difference between these two heights.
Yeah.
Why? Because A2 is less than A1. That implies V2 is greater than V1. That implies pressure will be P2 is less than P1. So because pressure is less, the fluid will rise comparatively less there.
Understood.
Okay, so here the formula for Venturi meter formula, the volume of liquid flowing per second through the wider tube. Okay, so what is the volume of liquid flowing? So the volume of liquid flowing will be equal to A1 A2 square root 2 P1 minus P2 rho A1 square minus A2 square. Okay, so this is the volume of liquid flowing through the Venturi meter. Okay, yeah, so which is equal to A1 V1 is equal to A2 V2. So that means this term is the Venturi meter is used to find the velocity, the free stream velocity. What is the velocity here at this point, at the entry point? What is the velocity? The Venturi meter is used to find the velocity at the entry point. So you know V is always, because of equation of continuity or conservation of mass, the so this is velocity actually. Okay, so this is velocity, not volume. Okay, so this is velocity A2 V2. Okay.
Okay.
So volume is equal to A1 V1 is equal to A2 V2. So this term is your V1, right? That the velocity, the free stream velocity. So this is the formula: A1 A2 into 2 into P1 minus P2. Okay, because P1 is greater than P2, and also you can see A1 is also greater than A2. That's why that formula. So 2 into P1 minus. So if somebody the velocity, so V1 is equal to square root 2 P1 minus P2 rho A1 square minus A2 square. So this you have to remember, that is, this is the free stream velocity.
Okay.
So the Venturi meter is used to measure the free stream velocity.
Understood.
Okay. So this is about Venturi meter. Okay.
Yeah.
So here all this equation of continuity and Bernoulli equation principle, those are utilized. Okay. And there are some other things like viscosity. Okay, what is viscosity? I was telling you, like viscosity. I was telling you modulus of rigidity. Okay.
Yeah.
That is nothing but your shear stress by shear strain. Okay, shear stress by shear strain. Shear strain, which is nothing but your shear stress, which is your F by A,
Yeah.
F by A, and shear strain is nothing but your like theta,
Angle.
right? Angle. So this is the theta or angle, which is nothing but your x by L or whatever. So when you have something like this, you are applying some force, it got displaced by like this. Okay, so this is your length and this is your x. Okay,
Yeah.
so your theta is nothing but your x by L. Okay, so
Yeah.
that is that is the shear modulus. Okay,
Okay.
shear modulus. But viscosity, that is for solids.
Yeah.
In liquid, the viscosity is nothing but your shear stress divided by strain rate actually. Strain rate. Okay, so this is dimensionless, but here it will be strain rate per second. Okay, so that will be tau divided by V by L actually.
Yeah.
Okay, so V is some distance per second divided by length. So that is the viscosity. So the viscous force is written by equation like this: F is equal to NA dV by dx. Okay, so that's what one is velocity, one is this. Okay.
Yeah.
So this N otherwise you can write as F by A, which is your shear stress, divided by dV by dx. Okay.
Yeah.
So this is your formula for viscous force. Okay. So this force F is viscous force. Viscous force.
Okay.
And this N is nothing but your coefficient of viscosity.
Yeah.
So only difference between the shear modulus and here is you have another, like here it is Newton per meter square, and below that you have to divide it by some second. Okay. Newton meter square by second. That the unit of shear modulus is Newton per meter square, whereas unit of viscosity is Newton meters per square second. And this equation is very, very important. The viscous force is equal to coefficient of viscosity into area into dV by dx.
Understood.
Okay. So this is the concept of viscosity. Okay. Okay. And there is something relating to this viscosity, this concept of terminal velocity and all. Okay. So that what is terminal velocity and all we can do it. Okay. So when a ball, when suppose you have liquid here, okay, so you have liquid here and a ball is falling down, okay, so a ball is falling down. So after some time, this ball will, because there will be a, when it is falling down, there will be a viscous force. So when the viscous force will balance out, then there will not be any acceleration and it will move with a constant velocity.
Yeah.
So that constant velocity will be called a terminal velocity. Okay. So this drag, the force which is dragging this ball will be, it will be 6 pi nRV. Okay. So this R is nothing but your radius of this ball.
Yeah.
Or the sphere. Sorry, ball or sphere. And V is your terminal velocity. V is your terminal velocity. So V is your terminal velocity. So this equation is otherwise called as Stokes law. Okay, Stokes law. So the viscous force when the ball attains terminal velocity is this much. Okay, so it is otherwise called the drag force on a small sphere of radius r moving through a viscous medium of viscosity. Viscosity. This is the viscosity with viscosity zeta with velocity v, terminal velocity v. Okay, and there is a equation for terminal velocity that is called Vt. Okay, that equation is 2 by 9 r square. Okay, 2 by 9 r square, then rho minus rho 0. Okay, into g divided by viscosity. Okay. So the terminal velocity is inverse. So what is terminal velocity? Initially the ball will be accelerating because the viscous force, the it will initially accelerate. Then after some time when it balances out, then it will be at constant velocity, no acceleration.
Yeah.
So that constant velocity is called terminal velocity. So there is a formula for the terminal velocity which is 2 by 9 r square rho minus rho 0 into g divided by zeta. Okay. Uh, okay, so there can be some numerical related to this. Okay, so somebody will say if the velocity radius of the sphere is 2 times, what will happen to terminal velocity? So you just remember terminal velocity is directly proportional to r square and it is inversely proportional to viscosity. So there can be some numerical what will happen to terminal velocity if the radius of this sphere doubles or whatever. So this is about terminal velocity and the Stokes law. Okay. These are some of the important things. Okay. You can take a picture. Okay. I'm not taking anything. So these are terminal velocity and
Stokes law.
Stokes law. Okay. Okay, so there is something called Renault number. Okay, what is Renault number? Okay, Renault number. This is also important. There can be numericals on this Renault number. So it's a dimensional less quantity. Because it is number, it's dimensional less quantity, and we write it as Re.
Yeah.
Okay, and its equation is rho V R by coefficient of viscosity.
Yeah.
Okay, so this is the formula for Renault number. Suppose you have a pipe. Okay, in this pipe, the velocity of liquid is V. Okay, and the density of liquid is rho, and the coefficient of viscosity of this liquid is zeta, and this radius of this pipe is r. If this is the case, this will be the Renault number. Okay, so that means if radius is high, then Renault number will be
directly proportional.
So rho v. So if the velocity is high, Renault number will be high. So if the velocity is too much, like say, okay, so there can be questions when Renault number is less than 3000, it is streamline flow. This is just a memory question. Okay, and when Renault number is greater than 5000, it will be a turbulent flow.
Yeah.
Okay, so there can be questions on this, or there can be questions to find a Renault number. Okay.
Yes.
Okay, so these are the major formulas related to properties of liquid. Okay, so having discussed all these formulas, in the next session we will solve some numericals. Okay, so you look at these formulas one more time, then we will solve some 5-6 numericals. Okay, for your practice.